Good day! Our topic for today is Introduction to Nuclear Fusion. So let's get started. Let's go! Nuclear fusion is a type of binary nuclear reaction. There are two types of nuclear reactions, but a nuclear reaction can be generally defined as the transformation of nuclide in contrast to chemical reaction, which involves the transformation of molecules. There are two main categories of nuclear reactions, namely radioactive decay and binary reactions.
Radioactive decay. Radioactive decay is a decay wherein there is a spontaneous breakdown of an atomic nucleus which results in the release of energy and matter from the nucleus. It also emits atomic nucleus particles or electromagnetic radiation that makes different isotopes of the same elements or an atom of a different element. A binary reaction is a reaction where two nuclear particles interact and transforms as one product. It occurs in two-step reaction. It is chemical vapor deposition or CVD and chemical liquid deposition or CLD. The energy released from this reaction is called Q value of the reaction.
The binding energy is the energy required to separate nuclei. It is observed that nuclear reactions do not conserve its reactant's mass. To resolve this violation of conservation of mass, the mass energy equivalence equation, or E equals mc squared, is used. Here are some examples of binding energy associated to some of the common fusion reactions, like isotopes of hydrogen.
Nuclear fusion. Typically, fusion happens at 10 to 300 times 10 to the 6th Kelvin. At this temperature, the reactant exists in a plasma state. The challenge in maintaining a fusion reaction is containing the plasma long enough to allow fusion reactions to produce more energy than it was required to start the reaction. Sustaining a fusion reaction. A fusion reaction requires the reactants to have high energy to begin fusing. To sustain a nuclear fusion reaction, the reactants must be contained so that the reactions can keep on happening.
There are three main ways that the reactant can be contained: gravitational confinement, magnetic confinement, and inertial confinement.
Gravitational confinement. A most spectacular display of fusion energy is associated with stars, where confinement comes about because of the gravitational pressure of an enormous mass. High density and temperature thereby result toward the stellar center, enabling the fusel ions to burn. While energy leakage and particle escape occurs from the star's surface, the interior retains most of the reaction power and prevails against the current radiation pressure through the deep gravitational potential wells, thus assuring stable confinement for times long enough to burn most of the stellar fusionable inventory.
While gravitational confinement is one of the main ways to contain the plasma needed for the nuclear fusion reaction, it is, as suggested, not a feasible method for us in practice. The two main methods used in nuclear fusion research today consist of the magnetic and inertial confinement, both of which have seen degrees of success and complications over time. The method of magnetic confinement makes use of the plasma's property of being electrically conductive to contain it through the use of magnetic fields. To recap, for fusion to occur, the reactants must have ample speed or temperature to overcome the electrostatic repulsion in the nucleus. The thought could be made that why don't we just put them in a metal furnace and contain them there? The required temperature for the reactants ranges from 100 to 150 million kelvins, of which no material can remain as a container at that temperature. To work around this, are reactors such as the aptly named tokamak for toroidal chamber with magnetic field, as the name suggests, uses magnetic fields to contain the plasma. The principle of magnetic confinement can be simplified by looking into the interaction between a moving electron within a solenoid. The solenoid produces a magnetic field, and the moving electron will spiral around within it in the direction of the magnetic field. The idea behind the tokamak is that it's a solenoid in a circle, so that the plasma within it continues to loop around the torus-shaped chamber to sustain the fusion reaction.
Inertial confinement. Nuclear fusion can be initiated by compressing a small fuel pellet, which usually contains a mixture of deuterium and tritium, to a very high density and temperature by an intense pulse of energy. This compressive pulse of energy may be supplied by laser beams or a charged particle beam. Both magnetic and inertial confinement fusion involve two key processes for the attainment of a viable fusion energy system. Number one is heating and ionization of the fuel to a high temperature to achieve a favorable fusion reaction rate density. And number two, the confinement of the fuel for a sufficiently long time to yield a net energy gain. Artificial fusion. Now, let us first discuss what is a fusion. A fusion is basically the energy source of the sun and stars. In the tremendous heat and gravity at the core of these stellar bodies, hydrogen nuclei collide, fuse into heavier helium atoms, and release tremendous amounts of energy in the process. Now in comes ITER. What is ITER? ITER stands for the International Thermonuclear Experimental Reactor, also known as the WEI in Latin, and it is one of the most ambitious energy projects in the world today. ITER is a 35-year collaboration to build and operate the ITER experimental device between the European Union, China, India, Russia, Korea, Japan, and the USA. It is currently under construction at Cadarache in the south of France. Its plasma volume will be 830 cubic meters. Its 13 Tesla toroidal field will be able to produce by superconducting magnets, and its diverter component is being designed to tolerate 3300 Kelvin. Now, what is the goal of ITER? The goal of ITER is, number one, to produce a 500 megawatt of fusion power. Number two, to demonstrate the integrated operation of technologies for a fusion power plant. And number three, achieve a deuterium-tritium plasma in which the reaction is sustained through internal heating. Number 4, test tritium breeding. And number 5, demonstrate the safety characteristics of a fusion device. Concurrent with ITER, the International Fusion Materials Irradiation Facility, or IFMIF, is planned to test the resilience of materials when subjected to sustained neutron bombardment. Its first tests were due to begin back in 2017. ITER and IFMIF will pave the way for the first full-scale fusion-powered station, DEMO, and the first commercial fusion power station, as a proto. Concurrent for DEMO are that construction will begin in 2024, and contributions to the power grid will start by 2040, whilst projections place proto post 2015.